Hello everybody and welcome to the next presentation of the GaiaX midterm event. This presentation is about a systematic SOTIF and credibility assessment. This assessment is a service composition built by the IQZ and SETLabs. My name is Fabian Plinke. I will do the first part of the presentation and the second part will be held by Maurizio Ahmann. The first question is, what is SOTIF? SOTIF is the safety of the intended function. Usually when we talk about safety, we talk about functional safety. So a component has a defect and this defect can lead to a critical situation. But let's say that every component is doing perfectly fine, but we still have critical situations. For example, a person is not recognized by the object recognition while crossing the street at a traffic light. This is a SOTIF case, and for highly automated vehicles, the intended function has to perform a very, very high level of safety. So functional safety and SOTIF are not replacing each other, they are extending each other. When we talk about functional safety, we search for random hardware failures or systematic failures in the technical system, which can lead to failures and to a malfunction. When we talk about SOTIF, we usually talk about environmental conditions and also foreseeable misuse and performance limitation to see if there are special triggering conditions without a system's failure that can lead to a malfunction. How can functional safety and SOTIF activities be integrated into each other? When we have a look at the standards, then SOTIF is a new case, so we have unsafe but reliable scenarios, and functional safety cases are unreliable and unsafe. There is a meta norm, the ISO 4804, and in this norm also cybersecurity issues are integrated because in modern development of highly automated systems, all these three areas, cybersecurity, functional safety and SOTIF, are analyzed together, but in this case we won't have a look at cybersecurity. So the question is how to integrate these two processes. And when we have a look at the V model and the steps of the functional safety process, we see that it's quite possible to integrate the SOTIF activities into the single steps of the functional safety process. And one very important point here is the hazard analysis and risk assessment, because here we can define our potential hazards and our critical scenarios. And these scenarios can be extended with a SOTIF point of view. And this makes it possible to combine these processes. And later we'll have a look how the verification and validation simulations can be added into the functional safety activities. We can demonstrate this with a little example. So for this presentation here, we've made a small example with an adaptive lane keeping system for a special ODD. And for this purpose, it's limited to highway usage and to a maximum velocity of 210 kilometers per hour. So to do the SOTIF considerations, we of course need the desired function. We need the ODD and, very important, the ODD limitations. And we need the system's architecture to see or to guess which environmental conditions can be critical for that special system. Here we have taken one scenario out of the functional safety HARA. So let's say our scenario is driving on the highway at a velocity of higher than 130 kilometers per hour. And our hazardous event now is an unmotivated deceleration by the ALKS in combination with the following vehicle with a small distance. So this is kind of likely event, so it's not very unusual. And the next question in the functional safety process is there a controllability given for drivers or the environment to control this situation? The controllability here would be that the drivers of both vehicles will act very, very sudden and try to prevent the crash from happening. The damage, if not, would be a rear impact with a velocity of higher than 40 kilometers per hour. So when looking at functional safety, we will try to figure out what system malfunctions or what component defects can lead to this unmotivated deceleration. From the SOTIF point of view, we now see, are there special triggering conditions from the environment that can lead to this unmotivated deceleration? So for perhaps we can have difficult weather conditions, rain, fog or anything like that. Or we can have perfect weather, but perhaps objects at the road edge which are not recognized correctly. So these can be triggering events from the environment, which can lead to our unmotivated or faulty deceleration. And also we try to figure out if the controllability can be enhanced. So perhaps if we have a driver who misunderstands or even misuses the function of the ALKS, the question is, can we redesign the system to prevent the driver from misunderstanding or misusing our ALKS system? The next thing is to see which options do we have from a SOTIF point of view to modify our system to limit the ODD or to monitor the driver, because these are the two major things we're looking at here at our SOTIF example. So to limit the ODD, we have to detect the ODD. So perhaps if we want to prevent the ALKS working when it's icy cold, then the question is the sensor capable of detect icing? And if the sensor is not capable of detect icing, then is the question, can we use some other higher system sensors or algorithms to limit the ODD? So for example, we can use the temperature sensor and limit the ALKS to temperatures above 0 degrees, for example. Of course, the improvement of the system itself, in this case the software algorithm, is an option, but let's say that this is quite expensive and not always unlimited possible. And then the third thing is to monitor the driver. When we say in this example here the driver has to pay attention to the road, then one possibility of making sure that the driver is actually paying attention is to monitor him with interior cameras. And now we need to verificate and validate this SOTIF concept to see if our system modifications, limitation of the ODD, improvement of the system, and monitoring of the driver has the effect that we need for a safe procedure here. So at first perhaps we can see if our improved object recognition works with a software in the loop simulation. Here we can see if our improved object recognition recognizes the objects very good in simulated weather conditions like rain and snow. The sensor self-detection for icing maybe can be simulated with a hardware in the loop simulation, and the system's reaction to our ODD, rain and snow, can be perhaps simulated the best with a vehicle in the loop simulation, where we can see the complete system's reaction. And so what we see here is that simulation is a very, very important part in the SOTIF verification and validation strategy, because without simulation it's quite not possible to get every scenario working or to just know how the system will react in very, very different situations. And so the simulation environment itself is very, very critical, and we have very high requirements for suitable, reliable, and safe simulation environments. And this, Maurizio, is your part for the second part of our presentation.
Yeah, thank you, Fabian. So this is actually a very important aspect. As this V&V strategy typically uses simulations, we need to raise the question, can we blindly trust these simulation results? So if the simulation results are not reliable, especially if they yield false positive results, the risk assessment itself is not reliable. And to understand what is additionally needed to make this risk assessment reliable, it is worth having a closer look at simulations in general. Why do we use simulations at all? So either we want to predict something that we cannot measure, for example, the CO2 effect on the global temperature, or we want to predict something that we could measure but we should not really measure, for example, if you will survive a crash in your car. In automated driving especially, we got the case that the effort to take for real measurements is not acceptable at all. So we predict how AD cars will behave by simulating certain scenarios. In the end, we always want to predict something. And there is an according simulation that claims to be in charge of making that prediction. So the important point here is, can we trust these predictions? Trust in simulation has similar limitations as trust in AD functions. We can only minimize the remaining risk of a false behavior. We cannot exclude this risk entirely, because there are too much physical effects, too much parameters, too much unknown confounders that cannot be considered entirely. Otherwise, the simulation would become too complex and the effort would not be manageable. So, this also means that a specific simulation is a representative of a system's behavior, not of the system itself. And therefore, validation of simulations must always be done context dependent. And this context is represented by this so-called claim. Now, to minimize this risk, we need evidence that gives us indication that the simulation's claim is not false. So, let's have a look at an example. We have a sensor simulation here during rain or snow. A possible claim could be that the simulation can be used in our SOTIF V&V strategy. A possible prediction of this simulation could be that the probability is below 0.1% that this sensor is triggering unmotivated deceleration in rain or snow. And I want to assess the risk that this prediction is unreliable. So I cannot really measure it, but by adding evidence, I know that I am minimizing my risk. So this evidence could be, for example, verification and validation of the simulation. And if I do this assessment systematically, we call it a simulation credibility assessment. But before we can make this credibility assessment, we should estimate what is the acceptable risk in the end. Can we take much risk or can we take only low risk? And for getting access to this question, let's consider some easy examples. We have 3 different simulations here. A simulation of indoor acoustics in a vehicle, a simulation of a reactor core in a nuclear plant, and a simulation of an electric fuse where we could predict, for example, a blowout current. And now by pure intuition, how would we rank the acceptable risk relative to each other for these use cases? So definitely the nuclear plant is the simulation with the most safety critical use case. A wrong decision could have fatal consequences here, whereas a wrong result for the acoustic system is more a comfort thing. And in the end we can sum up: the more safety critical the subject of a simulation, the lower the acceptable risk. And this leads us to the concept of the criticality assessment. A criticality assessment is the entry point for making a credibility assessment, and it tells us how much evidence we will need, or the other way around, how much risk is acceptable. By concept, it is done on a discrete scale of 3 levels, which we call credibility levels. And what kind of inputs do we need here? First, we need to have an estimation of a product-related risk, which means which bad events may happen, how likely are these events. We rate it internally on a scale of 1 to 10. And further, we need to assess how much influence does a specific simulation has towards the higher level decision in the product development. Here in our example, the higher level decision was if I can accept the risk that an unmotivated deceleration is triggered. And typically, this service is offered within a front end, which guides us through all of these steps. But if all of these inputs are already known, if they are existing because they are the result of the SOTIF assessment service, we could then automate our criticality assessment service. So let's have an overview again of our 3 services then. Our goal is to minimize the risk that simulations given in the V&V strategy of the SOTIF assessment yield unreliable results. For this, we want to use the credibility assessment. But before I can step into the credibility assessment, I need to evaluate how much risk I can accept. So therefore, for our service composition, we concentrate on the SOTIF service and the criticality assessment service. Typically, the criticality assessment service gets inputs from the SOTIF assessment that will look like the following depicted. And I'm picking up one of these examples of Fabian again, the unmotivated deceleration, which is a hazardous event. And for this hazardous event, we will have a V&V strategy. And that must be followed to minimize the acceptable risk that this event occurs under the given triggering condition. So, as we can see in our V&V strategy, there are 5 tasks to accomplish, and 3 of them are even simulation tasks. And let's pick out now one of the simulations, the simulation of the sensors and sensor fusion, to analyze the redundancy concept considering snow, rain and fog. As you can already see, it has a relative importance of 40% in this V&V strategy, so pretty high. So here we got an overview of all the required inputs for a criticality assessment service. So the hazardous event that an unmotivated deceleration occurs on the highway could lead to a rear impact with a delta velocity of more than 40 kph, and this could lead to people get injured, and even life-threatening injuries could occur here. So the severity of this hazardous event is rated to 3 according to the SOTIF and FUSA standard. And now we translate this in our internal table, which is pretty easy because this is a safety related case, and we even have a label here that tells us that fatal injuries would be rated a 10. Then next we have a triggering condition, and this triggering condition carries an exposure level according to the SOTIF and FUSA standard. The exposure level is a measure how often the triggering condition will typically occur. So this exposure level has been rated to 3 of 4, which means medium probability because weather conditions like rain or snow are not that seldom. So we translate it again to our internal table as 5, 6 or 7. And here I need to make an important note. For the criticality assessment, if you use simply safety-related use cases, you could also use ASIL levels for the estimation of the likelihood. But for the LKS, we got safety and SOTIF, so we calculate the probability of occurrence very conservatively using the exposure level. So finally, we are using the relative importance of our simulation towards the final statement that we want to make, which is 40%, which is very dominant, but it could not veto other results, so in our table it would be again a 9. So what we do here is then simply multiplying all our results, and the multiplication is called a criticality indicator, and we can map this to the required credibility level here according to our internal table. So finally, let's have a look what needs to be done to integrate these services as a service composition into the ecosystem. First, we need to finalize our input and output data structure between the two services. This is currently in draft. Next, we will create an orchestrated end-to-end demonstration of our service composition. And then, to make it work like it is specified in the GaiaX service composition model, which you can see on the left, we need to add information to the self-descriptions of the services that a potential discovery service can identify that these two services are matching service offerings. That means that they can be plugged together. So this can be seen here. This discovery service uses the self-descriptions to search for matching services. So, and this way, in the end, we can have a service composition where we can plug 2 or even 3 of our services, which is the ultimate goal in the end, together.